Hello and welcome back. We are now on Chapter 6, Part 2, and we are going to be talking all about the normal distribution. This is a really fundamental and important topic in statistics, so let's dive in. So we've been talking a lot about distributions, right? A distribution, again, it's just a set of numbers for whatever, it's a set of scores for whatever variable that you are collecting data on. So if you're collecting IQ data in a bunch of people, then the distribution is just all of the different IQ scores from all of your participants. And you can arrange all of those IQ scores into a frequency distribution, like a histogram, right? That's what we're looking at here. This is just a histogram. Now, the thing about some variables, just by nature, they are what's called normally distributed. Okay, and what does normally distributed mean? Normal distributions have one peak. They're unimodal, like what you're seeing here. They got one peak. They are symmetrical, and the mean, median, and mode are all the exact same value, and they're the value that's right in the middle of this. So it looks like in this case it would be 75 is going to be the value right in the middle of this distribution or of the possible range of scores. Okay. Now on the y-axis, we've got frequency, so that's what makes this a histogram. That's just how many participants got each of these possible scores. Let's say this is IQ, even though usually IQ is standardized to 100, so this isn't quite right. But anyways, normal distributions, there's all kinds of things that are normally distributed, right? There's things that most people will score the mean or around the mean, and the very few people will score far away from the mean on either side, right? So that's why you get the curve that starts low, goes high, and goes back to low again. Things like human height, blood pressure, ACT and SAT scores, the size of different snowflakes, the birth weight of babies, IQ scores, and job satisfaction ratings, all of those things are normally distributed. If you were to measure all of those things in a large enough group of people, you would see that some people are short, some people are very tall, most people are in the middle. Some people have low blood pressure, some people have high blood pressure. Most people have kind of a medium amount of blood pressure, right? A moderate. Some people score really poorly on the ACT or very highly on the ACT, but most people score kind of in the middle, right? So lots of variables in the world are normally distributed just like this. And that results in what's called a bell curve, or sometimes you've heard it maybe called a Gaussian, maybe Gauss. I'm going to say Gauss, a Gaussian distribution, which is just this nice bell-shaped curve. And lots of different variables, again, follow this normal bell-shaped curve. And I've chosen this image on purpose because it has bars to represent different buckets of scores, and the heights of those bars represent how many people have scored within that range of scores. But mostly going forward, we're going to be talking about the curve, which is just a curve that we can draw around these types of histograms and distributions. All right, so we're going to get a little bit more complicated now. So there are many variables that are normally distributed, right? They're symmetrical, they've got one mode that's right in the middle, right? And they start low, go high, and go low like a bell curve, right? But there's one standard normal distribution, okay? Or people just refer it to it as the normal distribution, right? It's like there are normal distributions. This one is the normal distribution. It is the standard normal distribution. And what you can see here on the x-axis, right, is that the mean is 0 and the standard deviations are always equal to 1. The standard deviation is equal to 1. Okay, that's why it's the standard normal distribution. It's always got a mean of 0 and a standard deviation of 1. And what's happened again is we've converted whatever the underlying variable is, take shoe size or something like that, converted all those raw scores into z-scores. And this is the standard normal distribution. But now this is actually more like a theoretical distribution. It's not as if we took a sample of raw scores and converted them into z-scores. This is more of a theoretical distribution if we had thousands and thousands or maybe infinite amount of people in a population. Okay, so standard normal distribution is more about populations, not so much about samples. The y-axis on a standard normal distribution isn't frequency anymore. It's not the number of people who got each possible score. It is something called the probability density function or probability density. And you don't really need to know like how that works. We will talk a lot about it today. But basically, instead of it being like absolute frequencies, this is a theoretical curve, a theoretical distribution. And we are asking the question, well, what is the probability that we would see a particular raw score or lower, or a particular raw score or higher? Okay, so now we're talking about, in theory, how likely is it that we would see a particular score show up in this distribution? That's why we're dealing now with probability and not really frequency. Okay, hopefully that'll make sense as we talk more about it. And remember the whole point, okay, the whole point of the standard normal distribution, number one, it's so that you can compare apples and oranges. You can compare two things that are on different scales. Now you can convert all of them onto the standard normal distribution and compare them in terms of numbers of standard deviations away from the mean they are. But we can also use this in hypothesis testing, which we'll get to in a couple of chapters. But basically, we can try to see, well, how weird is a particular score? If I've got a normal distribution of IQ scores, and then I get somebody who's like 3 standard deviations above the norm, which we'll talk more about what that means in a second, how likely is it that I would actually see somebody with that high of an IQ? Probably pretty dang low, because it's gonna end up in one of these small little tails on the right side of the standard normal distribution, where the probability of seeing something like that is very low, because the y-axis, the score on the y-axis will be very tiny. Okay, so let's talk more about that. So there's something different about the normal distribution, the standard normal distribution, compared to other types of z distributions. Because again, these are essentially made up of a bunch of different z-scores. That's why the x-axis is in units of standard deviations from the mean. But the thing about the normal distribution is that because it has a mean of exactly 0 and a standard deviation of 1 and a certain height, it has exactly 50% of the data on the right hand side. 50% of the data is above the mean, and 50% of the data is below the mean. And that's also because it's perfectly symmetrical and unimodal, right? So this is cool because it turns out that if you do some little math, you can figure out exactly which proportion of all of the scores in the population exist within 1 standard deviation of the mean, within 2 standard deviations of the mean, within 3 standard deviations of the mean. Now, why would that be useful? Again, the cool thing you can do with this, because all of the different areas under the curve are known, meaning all of the probabilities of obtaining a score between 1 standard deviation from the mean, or between 2 standard deviations from the mean, or 3 standard deviations from the mean. All that stuff is known. We know. And so you can see, if you take any individual raw score, you can compare it to where it's going to fall in this normal distribution. And then you can say, well, how weird, how unlikely, or how likely is it that we would see that kind of score? We'll talk more about that. But for now, what you can see here is in the standard normal distribution, if you're looking at just the percentage numbers on either side of the mean, remember the mean in the standard normal distribution is always 0 standard deviations from the mean because it is the mean. Well, you can see there's 34% of all the data points are going to fall between 0 and 1 standard deviations, and also between 0 and -1 standard deviation. So add those 34 and 34 together, and what you get is 68% of all the data points should fall within plus and minus 1 standard deviation from the mean. That means that already more than half of all of the data is going to fall within 1 standard deviation of the mean, right? Because that's where most people are going to score. They're going to score similar to the mean when you have a distribution like this. Well, you can go out further to plus and minus 2 standard deviations from the mean. So you can see that 13.5% of the data lies between 1 and 2 standard deviations from the mean. If you add all this stuff up, 13.5 plus 34 plus 34 plus 13.5, you get 95%. So that means that 95% of all of the people's scores for whatever you're measuring are going to lie between plus and minus 2 standard deviations of the mean. And what that means is that anything outside of 2 standard deviations from the mean is highly unlikely. It's very rare that you would ever see any raw scores 5%, right? Because the total area under the curve is 100% or 1. And if you have 95% of that data lives between plus and minus 2 standard deviations, if you get a score that's outside of 2 standard deviations, either -2 or +2 standard deviations, that's really, really unlikely that you would ever see such a score. Okay, so now we can get an idea of like, well, how weird is it that somebody has a shoe size of, 23 or something like that, right? That would be way, 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 way out there beyond 2 standard deviations. And you can say, that's pretty odd. Like that would be very unlikely for us to find something like that. This is a different graph, but it shows basically identical information. You can see that it uses slightly different percentages, so like 34.1% instead of 34, because all of these things have like rounding errors in them. And so if you look up the standard normal distribution online in Google and just look at all the different images, they'll give you very slightly different percentages. But this one goes out to plus and minus 4 standard deviations, and you can see what percent of the data is located between each of the standard deviations, and if you add them in the right way, it'll tell you how much is between, let's say, plus and minus 2 standard deviations, plus and minus 3 standard deviations, plus and minus 4 standard deviations. And this gives us something called the empirical rule, also called the 68, 95, 99.7 rule, which states that if you have a normally distributed distribution, that doesn't sound quite right, but a normally distributed distribution of you name it, whatever kind of heights or weights or standardized testing scores or whatever, and you put them all on a standardized normal distribution, or they naturally fall into a normal distribution. What you can say about that is that 68% of all of those data points are going to end up between plus and minus 1 standard deviation from the mean. 95% of those data points are going to end up between plus and minus 2 standard deviations, and 99.7% of all of the data points will tend to fall within plus and minus 3 standard deviations. So that means like almost all the data is within 3 standard deviations of the mean. So we can use this to say if we get a value that is like 5 standard deviations above the mean or 5 standard deviations below the mean, we can say, well, how likely is that to happen? It's incredibly unlikely because 99.7% of the data should be within 3 standard deviations. Anything falling outside of like even 2 standard deviations, which contains 95% of the data, like that's pretty unusual, right? And so we can use this to also start working on actually testing hypotheses about comparing certain sample means to other known population means, or 2 sample means to each other, and things like that using this normal distribution. All right, quick review question. Which of these z-scores is furthest from the mean? Well, that's going to be C, negative 2.30. That means it's 2.3 standard deviations below the mean. And that's essentially 2.3 standard deviations away from the mean. It happens to be below the mean, but that's much further, not much, but it is further than 1.79 standard deviations above the mean or 0.56 standard deviations above the mean. So let's walk through an example of this from the book. We have a distribution here, a normal distribution of final exam scores from previous classes. We see that the population mean is 75, so that's the final exam score average for all of these previous students. Now, let's say we have a new class, and the average final exam score for this class is 82. We want to know, using a standard normal distribution, well, how likely is it to see a sample mean of 82 in comparison to basically the population mean? So the population is the distribution of exam scores from all of the past students in this class, and that's represented by mu, right? Mu equals 75. The sample mean, which is just the newest class's average on the final exam score, that's x bar, and x bar equals 82. So how likely is it we would see such a sample mean given the previous population mean? So if we know the population mean and population standard deviation, we can transform that raw score of 82, which is the sample mean final grade. We're going to transform that into a z-score, which tells us how many standard deviations above the mean that is. And if you do the math, it is 2.33 standard deviations above the mean. So okay, so now we have the z-score, 2.33 standard deviations above the mean, but we want to know, well, how likely is it that you would see that kind of a score in this distribution? And we need a little help to do that. All right, so let's talk a little bit about probability and the area under the curve. All right, so this is standard normal distribution. It's a bell curve, and the total area under the curve is 1. Okay, it is 100% of all of the possible data under the curve, right? The area under the curve is 1, and the area under the curve you can look at for specific points and specific raw scores that you might be interested in. So let's say we're interested in measuring job satisfaction scores, okay? And those scores are normally distributed. And let's just say we find somebody who is just pleased as punch to be at their job. They're just super satisfied and they are loving it, okay? Whatever the job is, they're loving their job. And so it turns out, whatever the raw score is, maybe it's on a scale of like 1 to 10, you know, and they're scoring at a 9 or something like that. Well, if we convert that raw score of job satisfaction of a 9 out of 10 into a z-score and look at how many standard deviations away from the mean that is, let's just say it works out to be like 2.2 standard deviations above the norm. Okay. And so I've drawn this line here at 2.2 standard deviations above the mean for this population. And I want to know, well, what's the probability that you would see such a high score, given that most people, their job satisfaction is going to be 5, basically, if you're on a scale of 1 to 10. Well, there's a problem with that, okay? Because you can't find the area under the curve for one single value. All right, so if you think about this, this is a little theoretical. if you have a line, like I've drawn here, that represents a single value, single standard deviation away from the mean, well, a line has length but no width, okay? And so that means that it's not talking about really any area under the curve. So you can't actually find out what is the probability of having such a high score because you can't calculate an area under the curve. So what we have to do is we say, okay, I'm interested in knowing what's the likelihood of getting 2.2 standard deviations above the norm, but because that single value doesn't have any area, I can't calculate the probability. So instead I'm going to say, well, what is the likelihood of obtaining or observing a score of 2.2 standard deviations above the mean or higher? So I'm interested now in the probability that we would see people whose job satisfaction ratings are at least 2.2 standard deviations above the norm. So now what I'm actually saying is I'm interested in the probability that we would see a raw score, once converted to a z-score, that would fall anywhere in this little shaded area, this orange shaded area at 2.2 standard deviations above the mean and higher. So now we actually have area under the curve that we can find the probability of, because again, all of these different sections of the standard normal distribution are already known. They've already been worked out. And so basically what we need to do is to look up in a table, well, what is the probability of observing a value at 2.2 standard deviations above the mean or higher? And so there's something called a standard normal table, or sometimes you'll see it called a z-table, or I've even seen it called a unit normal table. Usually it'll have the word normal somewhere in there or z. And what this does is basically it just allows you to look up different standard deviation scores and see what percentage of the curve, what area of the curve, and therefore what probability would you have of obtaining that score or higher, or that score or lower. So let's get an example of that. And by the way, your book in the appendices has a standard normal table. And so let's get some practice on how to read those. Okay, so this is an image from the back of your book. I have the paper version, so forgive me that there's some smudgy stuff in the background. But what this is showing is the normal distribution, or the z-distribution. And it shows you this nice little image pointing to, when it's talking about the larger portion, that just means whatever side of the distribution that is, generally speaking, bigger than 50%. And the smaller portion is going to be whatever thing is smaller than 50%. So if you look at the very first row, at a z-score of 0.00, well, what is a z-score of 0.00, right? If z-scores are distance away from the mean in units of standard deviation, that means 0 units away from the mean, 0 standard deviations away from the mean. So it is the mean. It literally, a z of 0 is the mean. And so what makes sense is if you work your way to the right from that, it says the larger portion is 0.50 and the smaller portion also 0.50. That's telling you that because it is the mean, the percentage or the proportion of the curve, the area under the curve to the left is 0.50, 50%, and to the right is 0.50, 50%. That makes sense because it's the mean, so it's right in the middle. But let's take another value. Let's just go for a random one. Let's say 0.30. So a z-score of 0.30 means 0.3 standard deviations above the mean. And then if you work your way to the next column, which is the mean to the z-value, that's saying what proportion or what area lies under the curve, what proportion of scores lie under the curve between the mean and 0.3 standard deviations above the mean. That's 0.1179. So that would be, if you turn that into percentage, 11.79% of all the data points lie between the mean and 0.3 standard deviations above the mean. Go one column more to the right, and this is now the larger portion, okay? The larger portion is going to be basically everything below 0.3 excuse me, standard deviations above the mean. So that was, let's see, 0.6179. So 61.79% of all the data under the curve falls below 0.3 standard deviations above the mean. And 0.3821 is going to be 38.21% of all the data points should be at or above 0.3 standard deviations above the mean. Okay, so let's go back to that example where we were talking about exam scores from past classes compared to the average exam score for a new class. So the population mean exam score for all previous classes was 75. The sample mean, X bar, is 82. So we wanted to see, all right, well, how many standard deviations away from the mean is 82 compared to 75? And if you do the math, remember, we got 2.33 standard deviations above the mean. That's the average sample mean, the test scores for our new sample. Well, if we look up a z-score of 2.33 in the appendix on this standard normal table, it corresponds to, if you look at the larger portion, 0.9901. So that is going to tell you that 99.01% of all the scores lie below a z-score of 2.33, and only 0.99, less than 1% of all the scores, are at or above the sample mean of 82 and the z-score of 2.33. So if we were to, again, transform that sample mean final grade score of 82, we transform that into a z-score, it turns out to be 2.33 standard deviations above the mean. And if we plot that on this normal standard distribution, what percentage of the data points would be at 2.33 standard deviations or above the mean? And it turns out that 0.99% of scores would fall into that dinky tail, which includes everything at or above 2.33 standard deviations. This is less than 1% of all of the data in this entire distribution. This also means you can interpret this as we have a 0.99% chance to see a sample mean of 2.33 or higher, given that the original population mean was 75 and it had a specific standard deviation. Okay, so that means this is really, really, really unlikely that we would ever see such a high average final grade for a class. So what that means is that it's actually unlikely that the sample even came from this population distribution at all, meaning the sample of students who took the final and altogether got an average exam score of 82, they're probably somehow different from the population we were comparing it to, which is all of the previous classes, all the previous students from that class. So it seems like there's something actually different happening, and these two populations are significantly different in some way. But to actually be able to say whether they're statistically significantly different or not, that's where hypothesis testing comes in, and that's what we're going to talk about next chapter. Okay, what if you have a negative z-score, which means any of the standard deviations below the mean are going to be negative, right? So what if you have a negative z-score and you want to know what is the likelihood of obtaining a score below that or above that, right? Well, because the normal curve is exactly symmetrical, if you look at positive 0.40, the standard deviation, 0.4 standard deviations above the mean, it's going to give you the exact same proportions in either side of the under the normal curve, but they'll be like a little reversed from each other. And that's because, right, like if you're below 0.4 standard deviations below, then the smaller portion will be to the left and the bigger portion will be to the right. But if you look at 0.4 standard deviations above the mean, the smaller portion will be to the right and the bigger portion will be to the left, right? So you just kind of flip-flop those. So all you have to do is, again, if you want to see what the percentages of area to the left or to the right of a negative value are, negative z-score are, you can just look at the ones for the positive, but then you have to pay attention to, do you want to think about the proportion of scores in the larger portion or the smaller portion of the distribution? And we can get some practice with that in class. In a z-score distribution, the mean of the z-score distribution will always be blank. Yep, C, 0. The mean will always be 0 because if you do that z-score transformation and you look at the formula, subtracting the value of the mean from the mean will always give you 0, right? And so that'll always be 0 standard deviations away from the mean, which makes sense. If you think about a z-score as the distance away a value is from the mean, then if the mean, then the mean should be no distance from the mean. That makes sense. Okay, let's try something a bit more difficult. So what I'm interested in you finding is the proportion of scores, that is the area under the curve, between a z-score of 1.2 standard deviations above the mean and a z-score of 2.00 standard deviations above the mean. So in order to solve this, what you would do is you would go to your standard normal table or your z-table, and you would find, you'd look for 1.20 as the z-score, and you would want to find the proportion of scores in the large portion, okay? That's all the percentage or proportion of scores to the left. You would find exactly the same thing for a z-score of 2.00. You're looking for the proportion of all the scores to the left, so the proportion in the big portion of under the curve. And then what you would do is you would subtract the 1.20 area under the curve from the 2.0 area under the curve, and that is going to result in just this portion between the two z-scores. So what is that number? What is the proportion of all scores between a z-score of 1.2 and 2.0? So if you look up all the scores that are below 2 standard deviations, that's 0.9772. And if you look it up for 1.2 standard deviations, it's 0.8849. So if you subtract 0.8849 from 0.9772, you get 0.0923. That means that 9.23% of all the data is going to fall between these two z-scores. All right, let's end on a fun question. So I like this cartoon a lot. This is a love letter from a statistician, and the statistician is saying, you're 3 standard deviations above the norm. And the other partner says, thanks. And what this is saying is, of course, you are 3 standard deviations above the norm in terms of, being a good partner or maybe some specific attribute of that other person that this statistician is interested in and finds attractive. Okay, so what you need to do is look up in your book, or you could just look up in a z-table online. You could just Google z-table. What is the proportion of scores that lies at or above 3 standard deviations above the norm or above the average? So if you look it up in the back of your book and you find a z-score of 3.00, that corresponds with, in the smaller portion of the tail, which is going to be the proportion of scores above standard deviation of 3.00, you see the proportion is 0.0013. So that is way less than 1%. 0.13% of all the data is going to lie above 3 standard deviations above the norm. So what this love letter is essentially saying is you are so high above the average in terms of whatever characteristic I find attractive that there is a 0.13% chance that in any huge group of people that I would find someone as amazing as you. So hopefully the statistician's point is taken well by the partner. All right, that's it for this video, y'all. I'll see you in the next chapter.